phosphor?
12 inch? No.
The input phosphor is can be different sizes. There's a 12-inch, you can go smaller, 9-inch or 6-inch, but the output phosphor is typically 1 inch. Okay, 1 inch, so about the size of a quarter. So you're not going to sit there and look at a little teeny tiny image, right? You need to magnify it and be able to see it. What part of the eye, and I don't know how a question like this, I mean, I can ask several questions, but remember what they had to do, again, back in the old days, and again, before my time, what the radiologists had to do before they came into the Fluoro room, and that's what is that? Yes, they had those red goggles. That was to filter. To go from this light into a dark X-ray room takes time for the eyes to adjust, right? You know the minimum amount of time for the eyes to fully adapt to the darkness
15 minutes.
is 20. But the minimum amount, I mean, it takes, I think, 20 to fully,
10 minutes.
and I think 10 minutes to be able to perform an exam. So now that you're in the field, do you think a radiologist is going to walk into the room and everyone's going to hang out for 10 minutes while their eyes dark adapt? That's a year in radiology time, right? It's just not going to happen. So they would wear those red goggles. And so what they were doing, they were adjusting their eyes for their scotopic vision, which is what?
Is that your peripheral?
Nighttime vision. Pupils dilate. And what part of the anatomy, eye anatomy, are they going to be using for that nighttime scotopic vision? The rods.
Everything.
Everything in the eye. Well, of course, you use your whole eye, but primarily you're going to be using the rods. That was a problem, remember, everybody? Astronomers do this too. They don't look directly through a telescope to a star. They use their peripheral vision. And that is hard to do. That's a definite technique. So what do you think that whole concept of having to dark adapt the eyes, the room being dark, using peripheral vision, instead of looking at the screen straight on, they use their peripheral vision over here. So what do you think the problem ultimately is going to be for our patients? Or their patients? Yeah, more exposure. You know, if you can't see like you want to see, do you not take more time when you can't see something for whatever reason? Don't you have to look at it and deal with it, and it takes you a little bit of time? That's what happened to them. So how to make it better? So now we're able to use, with the image intensifier tube, it intensifies the image, and so they're able to use the cones, your daylight vision, your photopic vision, and to look at it with you can now see the image. We still dim the lights a little bit, but it's not dark in there. You can see what you're doing. And then cones are what's used for that. So much easier to see the image that we're looking at. Do you remember some of that? Okay, so some terms that we had before. Visual acuity is the ability of the eye to perceive fine detail, contrast perception, different contrast levels, and then the integration time of the eye is 0.2 seconds. We talked about that before. That means whatever the radiologist or you are looking at on a monitor, on a fluoroscopic monitor, that whatever you're going to see, you're going to see within 0.2 seconds. It doesn't get any better. In other words, the image doesn't build up on the back of your eye. Okay? The longer you stare at it, the better you can see it. That is not true. Okay, so if you cannot see something that you need to see on a fluoroscopic monitor in 0.2 seconds, then you need to change something. You either need to get closer, move the eye tube closer, increase technical factors, do something different. Don't just keep staring at something that's not going to get any better unless you physically change something. Okay? So that's what that means. We went over that already. Okay, so how does the eye tube increase the brightness of the image? And that is, there's a couple ways. Remember this flux gain? Minification gain. So a couple ways that this happens, this eye tube, is that, as an example, we start with one X-ray photon, it hits the input phosphor. That conversion is not a 1-to-1. It's like a 1 to 300, or different phosphors will give you a different ratio. But one X-ray photon, as an example, will create 300 light photons, which in turn from the photo cathode creates 1,000 electrons, and then here it converts it even more to 3,000 light photons. So here you have one X-ray, 3,000 light photons as an example. We're not memorizing these numbers. Those is just an example. Different books have different different numbers, and it all depends on what phosphor is being used ultimately. So so that is called the flux gain, the number of output light photons to the number of input light photons. So that is called the flux gain. The other is the minification gain. Now I talked about the input phosphor being 12 inches. It could be, you have the capability, or II tubes have the capability of having a 12-inch input phosphor. So the bottom of it is 12 inches in diameter, but that physically doesn't change, but we can make it act like a 9-inch and a 6-inch. Okay, there's not an iris where the input phosphor changes sizes. With the push of a button. It's a physical, solid piece of, phosphor. So, however, if you don't need a large II tube, you can get smaller ones. Maybe an orthopedic doctor who's his podiatrist, maybe he's just looking at feet or something like that, depending on who's using it. But minification gain is taking all that light from that input phosphor and then concentrating it and focusing it on that output phosphor. So you're taking all that light energy in a larger area into a smaller. So of course the light intensity would increase. Okay, so that's another reason. So that is your input to your output phosphor square. This is why I love the output phosphor being 1 inch in diameter. Because what is 1 squared? 1. What is 12 squared? Well, there you go. Aren't you smart? Good for you. Okay, so this, in the previous tests, I don't know in the test now, and I have some magnification formula questions, so that might be the next sheet. There's like 5 questions that ask. It's not like what is the amount, it's like how much more. If you go from a 12-inch to a 9-inch input phosphor, you go from 12 to 9-inch, how much minification gain is there? Kind of questions. So we'll look at that shortly. And then if you take the flux gain and the minification gain together, then that is the overall brightness gain. So both of those things together. So it says so basically the larger the number, the better the brightness. Now I've talked about this before, and I don't know if you'll remember, but none of that means anything unless you know what. I mean, I could try to sell you an II tube and go, oh, the overall brightness gain is 30,000. Wow, doesn't that sound great? Compared to 5,000, oh, you're like, oh yeah, I want that one. Boy, that'll be great. My staff will love it. But it may not be the best tube to buy unless you consider what. What causes any of this? What do you start out with? X-rays. So I can make this one brighter by doing what? Increasing the amount of X-rays. So what you really want to know is what
flux gain.
What you really want to know is the conversion factor. How much X-ray energy does it take to make that light energy? Right? Isn't that what you really want to know? That's the ultimate. Because we can all make our image intensifiers to as bright as it can be by increasing the MAs. So let's see. So it's the luminescence at the output phosphor. So the light at the output phosphor compared to how much X-rays it took at the input phosphor. So the luminescence of the output phosphor is CD. Do you remember what CD stands for? Candelas. Not candles, but candelas. Close enough. Per area. So much light per area. And then the input exposure rate, you know exposure rates are R, milli-R, per hour, per minute, per second, per rate of time. So that's the conversion factor. So that's anywhere from 50 to 300. So basically, the higher the numbers, the brighter it will be. Okay. Any questions on those? You have a question on your review exercise? Where, is that on there somewhere? Under which one? Oh, yeah, you could put output phosphorus, or is there a place for that?
We already have that.
Okay, yeah, light. Yeah, sounds good. I like that.
Hmm?
Light. Number 7, light. Is there anything else? Anybody else want to call it anything else?
What are we doing?
Yeah, I
No.
know. Okay.
No.
What?
She was looking at the
Magnification.
I2.
This is all we're turning into,
She was-
right?
No.
Oh.
That's just, she's looking at the number 7 on the picture. What did y'all put for number? What did you put? Mr. May, what did you put for number 7? Light. Okay, good. Okay, good, you had it. We're good.
Oh my
Yes,
God.
sir. I don't. Okay, let's talk about that. I had a few extras and I would give it to you if I had it, but other people have asked for them. You've got to bring, that's why I gave them to you. Maybe that was a mistake. You've got to bring all your stuff to class. Okay, remember, what did I tell y'all to do? Get a notebook, put them in, and bring it to class. I know, so it's okay. You can turn it in later, so not a problem, or another sheet of paper if you want to write the answers out, that's fine too. But I need you to bring this stuff because we will have opportunities to turn those in. We'll work on them in class, and then you can get points for those, or not. Or, so you need to bring your stuff, please, just as a reminder, because I gave out all the extras that I had. Okay. Multi-field tubes. So as I mentioned before, all the fluoroscopy tubes in your hospitals are probably either are probably multi-field, and so they can be dual focus or trifocus, and meaning they have the normal mode and then 2 mag modes are normal. I mean, erase that. Normal mode and 2 magnification modes are typical. Okay,
Mhm.
so here's what happens. Okay, wait, don't look. Okay, tell me about mag modes. When the doctor goes into a mag mode during a fluoro exam, what happens to the image? It magnifies. Okay, so 12, 9, or 6, which will give you the highest magnification mode?
6.
It's 6. So 12 would be normal. Then 9 would be a mag mode, and then 6 would be even more magnification. Okay, so here's why. That's why I wanted to see if you'd remember or not, and that's okay if you don't.
The focal point goes closer to the input phase.
Yes, the focal point right here.
How do you remember all this thing?
Oh, I don't know.
Studying hard.
No, it's just a bolt.
Or are you just reading
Here's what I've
ahead?
been for.
Okay,
Got you.
everybody, shh. Children, up here. Okay, so the focal point crosses sooner. The electrons are coming across. Here's a 9-inch and 6-inch. So this would be the normal mode, and then here is your magnification mode. The focal point crosses sooner, so therefore the divergence of the beam is
More. Bigger.
wider. So that's why the image is larger. Okay. So you can have 12 normal, then go to 9, and then go to 6, but each time. So my question to you will be, what happens during the magnification mode? You would say the focal point is closer to what?
Input phosphor.
Input phosphor, and further away from
Output phosphor.
the output phosphor. So watch the reference point. So you know those electrostatic lenses that lead up to the anode in the II tube? In mag mode, that KV it's like 25 kV plus, and so that increases, so it accelerates the electrons faster and they cross sooner. In normal mode, the electrostatic lenses, are 25, then in mag mode it may go up to like 35, that sort of thing, and it makes them cross faster, sooner. Okay, and so this is a picture I've shown you before. You actually have this PowerPoint in a longer version from last year. So this is what you're seeing. I just put a picture of a chest x-ray. So you're doing a fluoro of a chest, you see the whole chest. When you go into the mag mode, what happens is the electrons cross sooner, the beam is bigger, right? But the output phosphor size doesn't change. It's still the same size. This circle here is the same size as this circle. So you're only capturing what is hitting on this output phosphor. So therefore, if you're losing all of this electrons, what happens to the image brightness?
Goes down.
It will decrease. It will be darker. It
Less
will be
detail.
less bright. So do we like less bright?
Mm-mm.
No, we want to be able to see the image is darker, so therefore, what has to happen? So either MA increase, or KV increases, so we don't, back in the old days we had to, but now it's just automatically, you have that automatic brightness stabilizer where it kicks in and makes the image brighter. So what happens to patient exposure?
Goes up.
It increases. So anytime the doctor goes into mag mode, the patient exposure is increasing. If you're in the room with them, then the scatter reaching you increases also. So the doctors try to, or should try to, minimize their time in the mag mode. Fluoro in normal mode, an area of interest comes up, go into mag mode, take some images, static images of it, and then go back to normal, is how it should work. I don't know, have you seen any of your doctors fluoro in the mag mode the whole time?
The whole time.
Okay, so just something to think about. Okay. So here's a type of question, and I think that's one of maybe the next sheet in your packet of things. There's like 5 questions about magnification. So when operating the image intensifier in the mag mode going to 9 from 12-inch normal, how much more will the patient receive? So this will be in a factor. So the way it's figured out, you have normal mode squared and magnified mode squared. So what would be normal? 12, magnified 9. So 12 squared over 9 squared. You'd probably need your calculator for that. So what did you say 12 squared was? 144 divided by 81?
Mm-hmm. Anybody?
So 144 divided by 81, 1.8 times. So almost 2 times, not quite. A little less than 2 times. So just to give you an idea how much.
So it is 12 to 6 inch, like almost 4 times?
Yes, it'll be more. I don't know if it'll be 4 times. Let's see, 6 squared. So 144 divided by 36. Anybody have a calculator? 4, yeah. There you go. You were right. 4 times. Thank you. Okay, so what happens? Why do your doctors like the mag mode? I mean, yes, it's increased patient exposure. That's not why they like it, but you get better spatial resolution. You're able to see better. The image is larger. Better contrast resolution. The automatic brightness stabilizer increases, so you have more radiation. And isn't that true in CT also? That's where they get in trouble in CT, is because the higher the MA, or the higher the MA, then the better the image resolution is. And so they're not, whoever's reading the x-rays or taking the x-rays, that's what they tend to do to get better images. So there's a balance there. You've got to find that fine line to too much radiation based on the quality of the image. So anyway, this is what we want. This is why they like that mag mode. However, the pitfall is your higher patient dose, and then therefore not, that's a concern, but don't forget, that's potentially your dose and the radiologist dose if you're in there also. So let's look at your review exercises and answer those questions based on what the information I just gave you. So there's a list of questions. It's called basic operation procedures.
This one over here?
Some of these I didn't go over, but I will. So look at it real quick, go through, and you can work together if you want to, but answer the questions that you can. And then we'll go over them. It's front and back, so go through it and see. Go through it and see what you can answer.
Due to minimize the total X-ray beam on time.
Think about it, because you're letting the doctor look what's still in that mission save.
I put for points of interest. Oh, I guess I made up my answer. What does last frame will be? Is it probably the same? Is it going to save the image? That's what I don't know.
Yeah, if there's any that I didn't go over, you want to skip them, I'll cover them. Who wants to start answering questions? On the board.
Here, I'll do the first one.
Miss Kathleen, we're going to her killed over here. And then pass it off to somebody when you're done. Please.
Professor Nick.
I don't know anymore. No, give it someone else.
I'll take that out.
Oh, you just went and did anyone?
Oh, hey. You picked that up.
She didn't say I have to go
Raquel.
I made the next one down.
Oh, sorry. Oh, did I write on the wrong one?
No, I'm asking you.
And the reason she never activates, but now she said it's going to be like.
If you want to change an answer, I'm changing it.
Oh, she's telling me to change his answer.
Oh, am I wrong?
Oh, I don't know. I
I'm not listening to you ever.
Why did you listen to me the first time?
Who's next? Just go give it to them.
Throw it in the back.
Yeah, those people back there,
Those people, the back people.
What procedure can we use to keep the X-ray beam to the smallest practical size?
yeah, just scare them.
I'm sorry. I'm not looking like this. I'm just concentrating. No, I was doing great overall. Oh, I forget. Compared to other classes? Actually, you did overall really well. I was so pleased. Oh, I'm just, it's here at 9 and then 12. I teach it here at 7:30. You know, they like it. Maybe. Oh.
I know choice. Sorry.
I don't have any answer already done.
I'll remember that now. Byron, you're writing intimidating letters.
Hey.
Right?
Exposure and tell.
No,
I hope that's right.
Dun, da, da, da.
I forget how to use this.
Start now. I think we start live. I already activated. Oh no, sometimes.
Like a 4-year-old.
It's not our responsibility.
Wow.
Yeah. And we have one more of this for this part.
Your turn.
Number 9. Oh no, we know this one we didn't discuss, but you know that.
Using the last.
Oh, you didn't say my name.
Number 9.
They can compare it, right? What that means, do they compare to the current one to the previous?
Yes, they do kind of a road mapping
Yeah.
thing, but I mean, all your previous images you can see also. So let's go over what we have right now. What's the integration time of the eye? 0.2 seconds. What can the fluoroscopy? Listen, please. Fluoroscopy operator do to minimize. And that's true. Pulsing of the beam, intermittent. They can do that physically. The fluoro beam is also pulsed. It doesn't have to be, but typically it is pulsed. And then the stepping on the dead man switch and coming off of it, and that gives you that last frame hold, which we'll talk about in a second. What is the maximum time for the fluoroscopy reset timer? It is 5 minutes. What occurs is an audible sound, and there should be some interruption of seeing the image. So usually there's always a visual and an audible sound when making an exposure, or in this case, disruption of the exposure. What general exposure factors should be used during fluoroscopy? yes, fluoroscopy is usually 3 to 5 MA. What procedure can be used to keep the X-ray beam collimation? The radiation dose should not be. This is a true statement, but what makes this answer incorrect is this word right here. Okay, and I don't know that. We certainly didn't talk about it tonight, but let's review. Do you remember the 5 R per minute, the 10 R per minute with and without the AEC? Okay, so the maximum, at the tabletop, the fluoro beam should not exceed 10 R per minute if the automatic exposure control is on. Okay, now if the AEC is off, it can't exceed 5 R per minute. So so basically the regulators are stating that if the AEC is on, we trust the machine to do what it's supposed to do. So we allow this 10 R per minute. If it's up to us as operators, they don't trust us so much, and they keep it down to 5 R per minute. But we're going to do a demonstration towards the end of this class. Where are we in that's quite a bit of a range. A typical fluoroscopic procedure, a typical dose rate for a typical patient is 5. Even though we can go up to 10, most of them are in and around 5 for a typical patient. So that's what made that question different, and we really haven't gone over that. I think you go over that next class, don't you? Yeah, so you'll get more on that later.